All right, so today is a review session, so what am I reviewing? Transient, okay, so anything in particular? Like any problems in particular, Hannah?
Okay, I have an example.
Okay,
It's the fall.
all right, so let's open that up and see what's what. Move this out of the way. Old test. Open the file thing. Fall 2020.
So
Number 6. Is that a transient problem? We'll circle back around to that. I'm going to do a transient problem first because that was S.
On number 35 on the summer 2019 schedule, I tried to type in the whole equation on the calculator, they're typing it wrong. Why?
I don't know. I would have to see you do it. Like, come show me what you're putting into your calculator. I can't read your mind. All right, so you know what? I'm going to work the transient analysis problem or problems from this particular exam just because somebody asked about it. Right. So let's look at this guy right here. So the first thing that I can see looking at this particular circuit is that it's going to be a total response problem. Because the 7-volt source is always connected to the capacitor, right? So there's always going to be a source connected to our capacitor. So we are going to have some capacitor voltage at T is equal to, did I work this one as an example for you guys in class? I must work something similar to this. Are you sure I didn't work this for you over Zoom? This looks real familiar to me. Yeah, like VC at 0 minus is going to be negative 7 volts. This looks suspiciously like I think I already worked this one. All right, let's find something else. Sorry. Let's open up one of the other tests. Let's see, exam 2, winter 2019. Sure. That also looks very familiar. Son of a bitch. Let's do this one. I didn't work this one yet, right? Okay. So we draw this out. Or we can always just have you guys make something up and I can suffer through that as well. The op amp lab was done last Wednesday. Casey. $1K in series with $6K. We have 7 milliamps over here. And let's see how my switch is going to work. So switch is closed at A. Here's B, changes in this direction at equal to 0. Okay, so this is the circuit that we are analyzing. Everything look legible to you guys and all that kind of good stuff. All right, so the first thing that we're going to do is we're going to analyze our circuit at t is equal to 0 minus. I'm sorry, what? 3 kilo ohms, 1 kilo ohm, 6 kilo ohm. So at t is equal to 0 minus, we have our 4 milliamp source like so. Here's our 3 kilo ohm resistor. Since we're at DC steady state, because t is equal to 0 minus always represents a DC steady state condition, our capacitor looks like an open circuit. And let's just say we're going to find the capacitor voltage for this thing. Actually, let's see what the test said. Dang it, keep opening the wrong window. Capacitor voltage and resistor current. So let's solve for both quantities. Sorry, this should be 0 minus. So we should be able to do this step effectively by inspection, right? I say that, and then I'm going to ask somebody to do it, and then they're not going to get it. I'm going to feel like a jerk, but I'm going to do it anyway. Camille, what's my capacitor voltage at 0 minus going to be? The capacitor voltage at t is equal to 0 minus, what should it be? Annie, you want to help her out? Do it. 12. Yeah. So all 4 milliamps is going to flow through the 3 kilo ohm resistor. So 4 milli times 3 kilo is 12 volts. All right. Jackson, what's my resistor current at 0 minus going to be? 7 milliamps. Absolutely right. So not a whole heck of a lot of circuit analysis needed for our analysis at t is equal to 0 minus. All right, so let's look at things at t is equal to 0 plus. So at t is equal to 0 plus, our switch has changed from being closed at A to being closed at B. So our 4 milliamp source is still going to be there. Our 3 kilo ohm resistor is still going to be there. But now we're going to have an open circuit over here. And then this is where my capacitor is. Because we're at 0 plus, I'm going to represent my capacitor with a voltage source. So here's my resistor current, IR at 0 plus. The voltage source that is representing my capacitor will have the same voltage and polarity that my capacitor voltage had at t is equal to 0 minus. That's why it's positive polarity on top, and also that's why it's 12 volts. Since our capacitor voltage cannot change abruptly, we can write with no analysis whatsoever that VC at 0 plus has to be 12 volts, which is what we've substituted in here with that voltage source. So how do we go about finding the current flowing down through that 6 kilo ohm resistor? Killing me. So if we did superposition, which is a valid thing here, right? We could do simply Ohm's law to find the contribution of the 12 volt source. And then we would do current division to find the contribution of the 7 milliamp source. That's not too terribly bad. I'm going to say nodal analysis, or actually just Kirchhoff's current law, because that'll let me get it in 2 very simple steps, right? So if I consider, let me move this out of the way, change color. This node right here to be my reference. This is the only unknown voltage that I need to worry about. And so IR is just going to be whatever that VX is divided by 6 kilo ohms. But I can get that with just a single equation, right? So I would have VX minus 12 volts over 1 kilo ohm plus VX over 6 kilo ohms minus 7 milliamps is equal to 0. Solve that. Let me get a calculator out of my bag. So this is a 1 equation, 1 unknown system. So I'm going to use just my simple numerical solver here. So I'm going to have X minus 12 over 1,000 plus X over 6,000 is equal to 0.007. Solve. It's taking longer to do this than I thought. All right, I get the 16.286 volts. And from this, IR at 0 plus is VX over 6 kilo ohms. So I'm doing X over 6,000 in my calculator, and I get 2.714 milliamps. Kevin's suggestion of using superposition equally as valid. John's suggestion of using mesh analysis equally as valid. But this is a 1 equation, 1 unknown system, which I think is very easy to solve. And then Ohm's law, which I find very difficult to screw up. So that's why I went this particular route. Whatever method makes you comfortable is completely fine for you to use. Okay, so I want to be clear about that. I'm not trying to discredit John or Kevin. Their suggestions were perfectly valid. I wanted to do it this way because I feel more confident in my ability to not screw it up. That's it. Okay. So any questions regarding the analysis that we've done here? Just for safety's sake, let's check the answers. 2.714 milliamp seems legit. All right, so now we're analyzing at t is equal to infinity. So at t is equal to infinity, we're going to have the exact same circuit that we have at t is equal to 0 plus, but our capacitor is going to be at DC steady state again. So we replace the capacitor with an open circuit. So Here's our 4 milliamp source. In series and in parallel with our 3 kilo ohm resistor. We have our open circuit representing terminal A of our switch. This open circuit represents our capacitor, so this is the voltage VC at infinity. Here is our 1 kilo ohm resistor. Here's our 6 kilo ohm resistor through which our current IR at infinity will flow. And then over here is our 7 milliamp source. I'm going to pick on 2 Hannahs now. I'm going to pick on 1 Hannah now. Hannah Riddick, what is IR at infinity? Seven milliamps. Yeah. All right, Anthony, what's VC at infinity? I'm sorry, what was that? Okay. Jude, can you help me out? All right. Reese, I'm just gonna go around that damn table. All right, Justin. Finish your thought. Yes. So why is it 42 volts? I will explain it. I'm not going to make you suffer through that. Okay. So obviously there's no voltage drop over the 1 kilo ohm resistor because it's not part of a closed current carrying path, right? So we could say that this voltage is 0 volts by inspection. So that means that the capacitor is effectively in parallel with the 6 kilo ohm resistor. And since we know that 7 milliamps is flowing through the 6 kilo ohm resistor, 7 milliamps times 6 kilo ohms is 42 volts. And so we get 42 volts. So Justin was absolutely correct. All right, so now we need to figure out what our time constant is. So our equivalent capacitance is whatever the only capacitor in our circuit was, which in this case was 200 microfarads. This is enough room to figure out the resistance, I think. So to find our equivalent resistance, we need to look in through the capacitor's terminals with a dead network during the transient condition. So effectively what I'm going to do right here is I'm just going to redraw my circuit at t is equal to infinity and then turn my sources off. I'm looking at it at that particular instant in time because it's during the transient condition. My capacitor already looks like an open circuit. So now I just have to turn off my sources. So here's my 3 kilo ohm resistor. Here are the terminals of my capacitor. Here's a 1 kilo ohm resistor. Here's a 6 kilo ohm resistor. And both of my current sources look like open circuits because I've turned them off. So I'm looking in through the capacitor terminals, trying to find my equivalent resistance. And it will be what, Kirsten? I disagree. Carissa? 7 kilo ohms, absolutely, right? So the 3 kilo ohm resistor isn't really doing anything. It's just dangling off to the side effectively. So our capacitor at T is equal to 0 plus or greater really only sees a resistance of 1 in series with 6, which is 7 kilo ohms. From this, our time constant is simply the product of these two things. So that's 200 times 10 to the minus 6 times 7,000 is 1.4 seconds. And the inverse of our time constant is 0.714. No, I want to do a fraction. That's going to look like garbage. All right, so let's see. 1.4 is 7 over 5, so 5/7 per second. From here, we simply plug things into our generic equation, right? So VC as a function of time will be whatever VC at 0 was, which I believe we found it to be 12 volts for T less than 0 minus. And then we're going to have VC at 0 plus, which had to be 12 volts, minus VC at infinity, which we found to be 42 volts. So this is going to look like negative 30 e to the minus t over tau, which is the same as e to the minus t times the inverse of tau. So that's going to be 5/7 t plus VC at infinity for t greater than or equal to 0 plus. For our resistor current, let's see, we had 7 milliamps if I remember correctly. Then we had a number that I can't remember, 2.714 milliamps minus 7 milliamps. Double check that, yeah. 2.14. Thank you. And let's see, 2.714 minus 7 is going to look like negative 4.286. If my mental math is correct. All right. So transient analysis problem has been analyzed. So what's up? Sure.
So I'm trouble visualizing, so going to circuit. Then we could all do, of the gap right there.
Okay.
I guess what's, it's hard for me to that, I guess I don't. Why is there a voltage drop across?
Why is there a voltage drop across the open circuit terminals?
Is it the difference from that terminal to the other?
That is exactly what voltage is. Voltage is by definition the difference in electric potential between 2 points in a circuit. That is from the second day of class. Yes.
So we see it very same as I took that circuit from the show, took that thing out and shoved it on.
Yeah, absolutely. Yeah. So you're just measuring the voltage drop over the capacitor at infinity. So because I was out, we didn't get to do the lab where we literally do this, but we would be using an oscilloscope to measure the voltage as a function of time for a capacitor, and we would see that it effectively exactly matches the mathematical model that we've developed. An exponential decay or 1 minus an exponential rise as it charges. Any other questions on this or transient analysis in general or anything? I know some of you guys were watching some of my old videos and all that kind of jazz and saw that I had done problems using dependent sources in transient analysis problems. I have been told by the other faculty members that that's too mean, so it won't show up on your exam or anything like that. Yeah. Yes.
One off that just go for it. So the quick for who's gonna close at an infinite time later,
Uh-huh.
are we going to do anything for that?
On the exam, no.
Okay.
No, but for that, so for that particular problem, you're just doing transient analysis effectively twice. And so you do your transient analysis when your switch opens and it behaves one way, it's going to exponentially decay until the next thing happens, and then you have a new transient system. That's all it is.
So it's just different conditions essentially.
Yep, that's exactly right. So when that switch change states, it winds up adding a resistor in, which is going to change your time constant, which is going to change the rate of exponential decay. So it's going to look something like, graphically, what would be going on would be something like this, because it has a different rate once that resistor gets switched back in. That's it. John.
I don't think it's asked this, but time. This question saying like the minimum number of time.
5. We covered it in class. Yes.
There's a kid that's really nice.
Yeah, I did it in class so I did it in class on Monday, I believe. No, Monday was op amp, so that would have been Friday. At the very beginning of class. Yes.
But I heard when I was in like based on if the equivalent to the seconds,
200 micros, so that's 200 times 10 to the minus 6. Time constant will always be measured in seconds, just so that we're clear on why that is. Resistance is obviously in ohms, which is volts per amps. Capacitance is amp seconds per volt. So when we multiply these two things together, we get seconds. Similarly, inductance is volt seconds per amp divided by resistance, which is in volts per amp. So we have volts per amp over volts per amp, giving us just seconds as well. So time constant is always going to come out to be in seconds. But I do expect you guys to be able to handle the millis, micros, nanos. I don't think I'm going to give you anything with picofarads or anything like that, but 10 to the negative 12. Femto is 10 to the negative 15. Atto is 10 to the negative 18. And past that point, it's so damn small, I don't care. If it's smaller than a billionth of a billionth, it doesn't exist to me. They have effective mass, but that's well beyond the scope of this class. All right, what's next? Sure. So the exam to the Thevenin problem. All right, so we're going to take a crack at this guy right here. That is the wrong tab once again, so I'm going to make this slightly easier on myself and close out some of these tabs, so I'm less likely to make this mistake. All right, so we have a voltage source. Come on. Then that's in parallel with an 11 ohm resistor. That's the wrong tab, damn it. 2.1 amps directed to the right, 7 ohms directed to the right. Let's see. 8 in parallel with 5. Here's terminal A. Here's terminal B. And we want to find the Thevenin equivalent circuit, right? All right, so the Thevenin voltage. Is this voltage. So I would argue that nodal analysis would be the easiest thing to do here. Do you have a preference of where you would like to see ground placed? So make the ground terminal at A or on the other side of the current source. That's fine. So let's call this node A. Let's call this node B. And then make this one down here C, and I believe that's all of my nodes. Just to be on the safe side, I'm going to go through the trouble of identifying them. I don't want to work this poorly. So looks like I got at least the number of nodes correct and all that kind of jazz. So our Thevenin voltage is going to be whatever the results of our nodal analysis are, VA minus VB. Okay. So because of our choice for where ground was placed, okay. All right, so with this change, we can see from the jump then that our voltage relationship is going to be VA is equal to 8.4 volts. Now we're going to write a KCL equation for B and a KCL equation for C. Okay, so KCL at B is going to look like VB over 7 ohms plus VB minus VC over 8 ohms plus VB minus VC over 5 ohms is equal to 0. KCL at C is going to look like negative 2.1 amps plus VC minus VB over 8 ohms plus VC minus VB over 5 ohms. Just going to double check things here really quickly. So when I do it at B, I should have 1, 2, 3 terms, which I do. VB over 7, B minus C over 8, B minus C over 5. All right. When I write my KCL equation at C, I will also have 3 terms, this one to the left, this one down, and this one down. Negative 2.1, C minus B over 8, C minus B over 5. All right. So now I just need to solve this system. So that's what calculators are for. So in my second equation, my coefficient for VB is 1/7 plus 1/8 plus 1/5. My coefficient for VC is -1/8 minus 1/5. I'm putting it in the wrong column. And I hit the wrong button on my calculator. Different one. All right, so my coefficient for VA is 0. 1/7 plus 1/8 plus 1/5. -1/8 minus 1/5. Constant term is 0. My coefficient for VA, I am that lazy that I'm writing VA in my 3x3 system, just for you guys. My coefficient for VB is -1/8 over 1/5, or excuse me, -1/8 minus 1/5. My coefficient for VC is +1/8 plus 1/5. Constant term is 2.1. Solving, I get VA is 8.4 volts. VB is 147 over 10, so 14.7 volts. VC is 2751 over 130 volts. From this, my Thevenin voltage is VA minus VB. So X minus Y, -6.3 volts. Let's see if that matches up. I'll be damned. Yes. Because VA is the node associated with the positive polarity terminal of our Thevenin voltage, and VB is the node associated with the negative polarity terminal of our Thevenin voltage. So it's VA minus VB. Nope, not at all, because we're dealing with nodal voltages. So it's just the difference between those two nodes. And because A has the positive polarity terminal, it gets the plus sign. B has the negative polarity terminal, it gets the minus sign. We could suffer through writing KVL equations all over the damn place and we'd wind up getting the exact same result. The beauty of nodal analysis is that because a voltage is simply the potential difference between 2 points, and we know the voltages at every different point in the circuit, we can just take the difference. Kevin. Yep.
Wait, why is that 11 over disconnect?
So two reasons, really, they're kind of the same thing. Okay. So we have a supernode that contains our voltage source, right? Because anytime we have a voltage source and we're doing nodal analysis, we are going to have a supernode. Because our supernode contains ground, we don't write a KCL equation.
Okay. Well, they didn't contain ground.
Yes, we would, absolutely. So with the original choice of ground, we would have found the 11 ohm resistors showed up in our equations. Okay. Now, technically speaking, anytime that you have a resistor in parallel with a voltage source, that gets lumped into the supernode. The reason being is that the current is going to flow. So let's say that our ground was somewhere else. Okay, just bear with me here just a moment. So we would be writing a KCL equation for all of the currents leaving this supernode. We have the current flowing down through the 11 ohm resistor and the current flowing up through the 11 ohm resistor, which are going to cancel each other out. So the 11 ohm resistor still won't really show up in our equations because it's in parallel with the voltage source.
And then
8.4 over 11 going up and 8.4 over 11 going down. Yeah.
Right.
Yeah. So it makes a lot of sense to me, but anyway. I'm a jackass with a PhD who's been doing this for far too long. All right, what's the next question? What are we looking at? The fact that I asked for the Thevenin, that's it. Every circuit is a Thevenin Norton circuit. Yeah, well, so absolutely. Okay. As a matter of fact, I used it yesterday with my ICE-T students to simplify the equivalent circuit of an induction motor down to something that's less of a pain in the ass to analyze. So we're not going to go through the nitty-gritty details here effectively, but I'm going to explain how you could use it to make your life easier. Because Thevenin and Norton equivalent circuits are also used a lot when you're analyzing transistor-based amplifiers to make simplifications to your circuit. So an induction motor has the following equivalent circuit, and you'll have to bear with some of my notation here because you don't know what it means just yet. X1, sorry. Same notation. Now, in an induction motor, it's a three-phase system, so this is a per-phase equivalent circuit. You don't need to write literally any of this down, by the way, okay? But we have this circuit, which is operating at some particular angular frequency and some particular slip. So analyzing this thing to try to figure out like what our rotor current is, what our stator current is, and all that kind of stuff can be a bit of a pain in the butt. This is a simple circuit that you could use with just two meshes, but using meshes in the frequency domain requires us to use a computer to solve it, because the calculators that we're allowed to use in this class and in that class literally can't solve systems of equations using complex numbers, which is going to be a pain in you guys' butt in about a week. Okay. So instead, we can use a Thevenin equivalent representation in order to simplify this thing. So what I mean by that is if we disconnect the stator part of the circuit, which is everything to the left of that blue line, and replace it with its Thevenin equivalent, we will have this circuit. Which is a simple single loop circuit that's very trivial to analyze. Doesn't require computers or anything fancy, just good old Ohm's law, and we're good to go. So that's Thevenin equivalent circuit, replacing something that's hard to deal with and making the overall circuit more simple. We do that all the time when we're doing small signal analysis of transistor amplifiers as well. Because we have this big gnarly looking thing, but we can compartmentalize and simplify that's by Thevenin equivalence. Once we go through, steady state sinusoidal analysis, I'll actually work a couple of examples where we'll simplify things using Thevenin equivalent circuits to avoid having to use mesh or nodal or anything like that. But for right now, it's a Thevenin circuit. If I tell you, give me Thevenin voltage, Norton current, or Thevenin resistance. But it is, can be used as a very powerful circuit analysis tool. Any two-terminal linear electrical network can be replaced at the terminals by a Thevenin equivalent circuit or a Norton equivalent circuit. So we just have to have a two-terminal network, and then we can apply it wherever we want. And we get to make up terminals if we need to, which is what we did here. Yes.
So, circuit we just did, test.
Yeah. And then we would measure the current through the short, but I would argue that that's going to be a 4 mesh thing. So just clear here. Our Norton current will by definition be this current. And the knee-jerk reaction to something like this would probably be to do mesh analysis, which would have 4 mesh currents. Some of you guys' calculators can take care of that. Some of you guys cannot. One thing that you could do to make life slightly easier is recognize that now node A and B are the same node. And so nodal analysis would literally just be solving for node C, and then we could figure out our currents using Kirchhoff's current law. Or you could just find the equivalent resistance and then divide the Thevenin voltage by the Thevenin resistance to get the Norton current, which would probably be the way that I would go because it seems like less work. Yeah. So, all right, what is next? Yes, Justin. No, because the 8.4 is between A and ground. And the voltage drop over the 8 and the 5 ohm resistor is between A and C. So because C isn't grounded, they're not going to have an 8.4 volt drop over them. I would argue they're going to have a voltage drop of whatever 2.1 amps times 8 in parallel with 5 is. Okay, John, you had your hand up a moment ago. What did you say, fall 21? I don't know. So number 12, right? All right, so I'm just going to scribble on this. So this is a DC circuit. So our inductor looks like a short circuit. So this is going to be our inductor current IL, and our capacitor is going to look like an open circuit. So this is our capacitor voltage, VC, right? Let me think about this. So you said you found IL, right? Okay. So I would argue that these two resistors are also carrying IL because they have to be. None of it can branch off and flow down through that middle left branch. So I would write a Kirchhoff's Kirchhoff's voltage law equation around this loop. So you'd have negative 24 volts plus 28 IL plus VC plus 9 volts is equal to 0. Solve for VC, and then 1/2 CV squared gives you the energy stored by the capacitor. That is problematic. What's next? All righty, well, you guys can enjoy the rest of your Friday. We're gonna have another review session on Monday for the test. So like Monday during class time. So study over the weekend. If anything doesn't make sense, come ask me on Monday.